Hi, welcome to the Terracotta ehcache consistency screencast. I'm Abhishek Sanujam, software engineer at Terracotta, and I'll be talking about the new ehcache consistency modes introduced in the latest ehcache release. ehcache 2.4 with Terracotta 3.5 was released just a few days ago. Lots of new cool features were added into this release, for example, search, new consistency modes, non-stop feature, rejoin, explicit locking API, and various other perf improvements and bug fixes. Please visit ehcache.org to find out more details about this release. Today, I'll be talking about the new ehcache consistency options introduced in this release. A new attribute consistency has been added for Terracotta clustered caches. You can specify the attribute in the Terracotta element for each of your Terracotta clustered caches in your ehcache.xml. The attribute can take values of strong or eventual. The old coherent attribute has been deprecated and the new consistency attribute should be used instead. With strong consistency, changes made by any node are visible to all the other nodes in the cluster instantly, while with eventual consistency, changes made by any node are visible to the other nodes eventually. You can go to the link ehcache.org/documentation/terracotta/consistency_options.html to read up more about the various consistency modes. Let's talk about these modes in a bit more detail. With strong consistency, changes made by any node are visible across the cluster instantly. Reads and writes with strong consistency are done in the Terracotta clustered logs, which are same as normal read-write logs, but they are valid throughout the cluster. Multiple reads are possible throughout the cluster concurrently, while writes are mutually exclusive to other writes and reads happening in the cluster. It always happens before semantics across the cluster, which is a result of using Terracotta clustered logs. It supports concurrent APIs in the ehcache interface like put if absent, remove element, replace, and replace with two argument. It also works with explicit locking APIs. Eventual consistency. With eventual consistency, changes made by any node are visible throughout the cluster eventually, which is normally in the order of milliseconds. When changes happen, the Terracotta server, which is called the L2, notifies the clients about which keys were updated, and the clients, which are called L1, upon receiving the notification from the L2, removes those mappings from its local cache. There is a small window in which, even after some other client has updated the values and before the L2 has sent out the notification for those updates, the client can still read stale values from its local cache. So, eventual consistency is normally suitable for apps that can tolerate reading stale data for some time. Also, for read and writes with eventual consistency, there is no need for clustered logs, which results in better performance compared to strong consistency. It also supports concurrent APIs in the ehcache interface and also works with the explicit locking APIs. The old coherent attribute has been deprecated and the new consistency attribute should be used instead. For apps already using the old coherent attribute, coherent is equal to true will translate to consistency is equal to strong, which behavior-wise is the same thing. And coherent is equal to false would translate to consistency is equal to eventual. Coherent is equal to false used to mean bulk load mode, which is now no longer possible to set in the config but can be enabled through APIs only now. Bulk load mode or the old coherent is equal to false mode. Like eventual consistency, no locks are required for reads and writes with bulk load mode. Writes are batched heavily in the client, and as the name implies, warm-up of large caches happens pretty fast in this mode. For reads in this mode, once the values are fetched by the clients, the updates made by other nodes are only visible after a specific period of time, which is 5 minutes by default. And from this release onwards, it is possible to enable bulk load mode through APIs only. The old APIs have also been deprecated and the new APIs introduced in each cache interface should be used. Let's now take a look at how it's going to work with an example. Let's say there is one Terracotta server and three application nodes in the cluster, node A, node B, and node C. Now, let's say node A does a put of K1V1 into the cache. As its strong consistency, it's going to acquire a write log before doing the put. It will ask the L2 to grant the write log. The L2 in turn is going to check if any other node in the cluster has acquired a lock for the said key. And as no other node has acquired a lock for the key, it's going to grant the lock to node A. Node A, after getting the lock, is going to go ahead with the put. Now the put is going to get persisted in the Terracotta server. Node A is also going to keep the mapping in its local cache. Now let's say nodes B and C does a get for the same key K1. As reads also need locks with strong consistency, both the nodes B and C are going to ask the L2 for a read lock. The L2 in turn is going to check if some other node has already acquired locks for the same key, and as locks are granted greedily in Terracotta, it's going to ask back the right lock from node A. Node A is going to give back the right lock, but since the recall is happening for the read level lock request, it's not going to clear its L1 cache. The L2 then goes ahead and grants read locks to both nodes B and C. Nodes B and C then goes ahead with the get and fetches value V1 from the L2 and then populates it in its local cache. Now let's say node A updates the value to V2 by putting K1 V2. And since it's a write operation, it's going to ask the L2 for a write lock for the same key again. The L2 is then going to recall the read locks granted to nodes B and C. But since the recall is because of a write level lock request, all the L1s are going to clear its local cache of the corresponding key. The L2 then grants a write lock to node A, which in turn goes ahead with the put. The L2 now has updated value of K1 V2 and node A is also going to update its local cache to K1 V2. Now let's say nodes B and C does a get for the same key K1. As it's a read operation, it's going to ask the L2 for a read lock for the same key K1 again. The L2 is then going to recall the write lock granted to node A. But since the recall is happening because of a read level lock request, node A is not going to clear its local cache. The L2 is now then going to grant a read lock to both nodes B and C. Nodes B and C will then check its local cache to see if a mapping exists for the key K1. And since it doesn't exist, it's going to go to the server to fetch a value for key K1. It will get the updated value V2 for key K1 from the L2 and also update its local cache to contain the mapping K1V2. At this stage, all the nodes A, B, and C has read locks for this key K1 and also has a mapping K1V2 in its local cache. And if gets happen for the same key K1, it's not going to go to the L2 because it already has a read lock and hit the local cache returning V2. That's how strong consistency works. Now let's take a look at how eventual consistency will work. Let's take the same use case with one L2 and three client nodes, node A, node B, and node C. Node A does a put of K1V1 and since it's eventual consistency, it doesn't require any locks and just does the put directly to the L2. The L2 persists the mapping K1V1 and node A also updates its local cache to K1V1. Nodes B and C does a get for the same key K1 and since it's eventual consistency, it goes directly to the L2 after checking its local cache and then fetches a value V1 from the L2 and also populates the mapping in its local cache. Node A updates the value for K1 by doing a put of K1V2. It directly goes to the L2 as no write locks are required for eventual consistency. The L2 updates its value to V2 and node A also updates its local cache to contain K1V2. Node B and C does a get for the same key K1 and since the L2 has not yet sent out a notification that the mapping for key K1 has been changed, both the nodes are going to read from its local cache V1. Eventually, after some time, which is normally in order of milliseconds, the L2 is going to send out notification that the mapping for key K1 has been changed to value V2. Nodes B and C, on receiving the notification, is going to remove the mapping of K1 V1 from its local cache. When gets happen for the same key K1 from nodes B and C, it's going to see that its local cache doesn't contain the mapping for key K1 and it's going to go to the L2 to fetch its value. The L2 is going to return the updated value V2 and nodes B and C is also going to update its local cache to contain the mapping K1V2 and return V2. If subsequent gets come in for the same key K1, it's going to hit the local cache and return V2 directly. That's how eventual consistency works. That ends the presentation for today. You can always visit the website terracotta.org or ehcache.org to find out more information. Thank you for watching.